Welcome to our physics lesson. My name is Nicholas Okuthe. We were looking at floating and sinking as a topic in our previous lesson, and we want to proceed from where we left. Now, we want to look at the last aspect of this topic called applications of Archimedes principle and relative density. In our previous lessons, we have looked at hydrometer in details, but maybe just to repeat what we have already done. Hydrometer is a device that looks like this and is used to measure or to determine relative densities and densities of substances. So it means it can measure relative density, it can also measure density of any substance. We said it has a narrow stem, and the reason why it's narrow is to make it more sensitive. The scale runs from minimum value up there to the maximum value down there. It has a wide bulb to make it displace large volume of the liquid, therefore providing sufficient upthrust to make it float. Then it is weighted at the bottom, meaning it has lead shot, or it can be sand or anything heavy to make it float upright in the liquid. So we also said that it sinks more in a less dense liquid and sinks less in a more dense liquid. We have different types of hydrometers. We have what we call the lactometer. Lactometer is the hydrometer used to measure relative density of milk. If you want to know the purity of milk, then you use the lactometer. And the range or the scale ranges from 1.015 to 1.0045. So it is that short range. So anything outside that range makes the milk impure. Either below means it has more water. More water. If it is above this, then it means there are other contents that have been added to it. We have brewer's hydrometer used to measure relative density of alcohol or beer. So the companies that make beer know the purity or determine the purity of the beer by using the brewer's hydrometer. Then finally we have the battery acid hydrometer. This one is used to measure the relative density of sulfuric acid in the car battery. So, under the maintenance of an accumulator, the acid should be topped up when it reaches some level. So, how do you know that level? So, you can know by looking at the mark or by using the battery acid hydrometer. The second application is the balloon. And balloon, one that are used by meteorologists, where gas which is less dense like hydrogen or helium is used. Balloon moves upwards because upthrust force is greater than the weight. So it can only move up whenever upthrust is greater than the weight. Then it rises to some height where the density is equal to that of the balloon. At this point the balloon stops rising because upthrust is equal to the weight, and therefore the resultant force on it is zero. The density of air, as you go up, the density of air reduces. So that reduction will make the weight of the balloon material and the balloon, the air inside it, the gas inside it, to be equal to the upthrust. And when the upthrust is equal to weight, there will be no net movement of the balloon, so it will remain afloat in the air. The second or the third one is called the ships. Ships are normally made of steel, but steel is denser than water. And if you take a piece of steel needle and you immerse it in water, you will obviously see it sink. But why is a ship able to float? They are able to float because of their shape. They are made hollow. They are big in size and the space inside is wide. So when they are hollow, they displace large volume of water. The large volume of water will provide sufficient upthrust. That sufficient upthrust is able to support its weight and make it float. Now, the average density of seawater is normally greater than the density of fresh water. Fresh water is around 1,000, seawater is probably 1030. So, due to this difference, and a ship may be moving from fresh to seawater, sea to fresh, they are fitted with something called plimsoll lines. These plimsoll lines on the sides of the ship show the level to which it should sink in fresh water and the level to which it should sink in seawater, so that if at all there is a difference, then danger is noted and necessary corrections can be made. For example, maybe if the level on seawater has been marked and the moment it enters seawater, it sinks beyond that level, then it means that there is some problem. So a correction has to be made before accident is caused. Finally, we have something called a submarine. A submarine is just the same as a ship, but the difference is that a submarine can float and sink at the same time. It can decide to sink, it can also decide to float. So that floating or sinking enables or can be determined by something called ballast tanks. Sometimes, or some books call it flotation tanks. So submarine has those ballast tanks, and the ballast tanks can be filled with air or water to some height. For example, if you want it to sink, then the ballast tanks are filled with water so that the weight is greater than upthrust. If you want a submarine to float, then the ballast tank is compressed so that it is only filled with air. Yeah, so only air is allowed into the ballast tank. So that way, upthrust will be greater than the weight, and the submarine will be able to float. Yeah, so there is a calculation on hydrometer that probably you need to understand. For example, we have this hydrometer of mass 20 grams floating, oil of density 0.7 grams per cubic centimeter, with 5 cm of its stem above the oil. If the cross-sectional area of the stem is 0.5 cm squared, calculate the total volume of the hydrometer. So hydrometer floats. So we apply the law of flotation, and in the law of flotation is what will enable us make this kind of calculation. In the law of flotation, the weight of the hydrometer will be equal to the weight of the oil displaced. So the first question, total volume of the hydrometer. Yeah, so volume of the hydrometer is the same as the volume of the oil displaced. So volume of oil displaced will be mass of the oil over density of oil. Mass of the oil is the same as mass of the hydrometer because it is floating. Weight of the oil is the same as weight of the hydrometer. So mass of the oil is the same as the mass of the hydrometer. So we take 20 divided by 0.7 and note the views here 0.8, but it should have been 0.7. So you get that. So volume of the hydrometer above the oil will be the 5 cm remaining times the cross-sectional area. So that will be 5 times 2.5. So this volume is inside the hydrometer, while this one is above. So total volume will become the volume inside plus the volume above. That gives us 27.5. Length of the stem of, out of water if it floats in water. So if it floats in water, it will displace the same mass. So mass of the hydrometer is that. Weight of the hydrometer will be 0.2, which is written as 2 times 10 power negative 1. So weight of water displaced will also be the same because it is floating in water. So the same weight of the hydrometer. So mass of water displaced will just be 20 grams. So volume of water displaced will be the mass of water divided by the volume. So that gives us 20 centimeters cube, not 20 grams per centimeter cube. It is 20 centimeters cube. That will be the length or the volume that will be floating in water. So if we want the length that will be floating in water, we take the volume, we divide by the cross-sectional area. So if we take probably 20 divided by 0.5, then you'll be getting around 4 centimeters, being the one that is outside the water. If it floats in water, you take the volume, you divide by the cross-sectional area to get the length. There's also this one, hydrometer of mass 20 gram float. Sorry. I think the same calculation is given there. So we could have these kind of questions to enable you practice more on this. From this number 2, when a body of mass 450 grams completely immersed in a liquid, the upthrust on the body is 1.6 Newton. Find the weight of the liquid. Number 2 is on testing on Archimedes principle and moments. The figure below shows an arrangement with the rod balanced by a knife edge at the center of gravity. The 5 Newton weight on one side balances solid S. The volume of solid S is given as 100 cubic centimeter, which lies immersed in a beaker of water on the other side. The beaker of water is then removed, and while keeping the 42 centimeter distance constant, the position of solid S is adjusted to obtain the balance point. Again, determine the new position of S. So you just apply the principle of moments. What would be the new position if it was immersed in a liquid of relative density 0.8? So you could try that to enable you go through this topic. So that is the end of this topic. I believe we'll be able to meet again and do more. Thank you.